Okay, so let's recall that in the previous video we proved that two straight lines in the plane of f that are intersecting in the real plane intersect at a point in the plane of f itself. More precisely, if f is a subfield of the field of real numbers and you consider two lines in the plane of f, what that means is that you consider two lines like this such that each one of them passes through 2 points whose coordinates, for example, this is 1 point, whose coordinates, real coordinates are say a comma b, and both a and b are coming from the subfield f. In other words, this ordered pair is coming from this Cartesian product. Then such a line, and there would be another one such point which also is coming from f, Cartesian product f, then such a line we call a line in the plane of f. Just like this Cartesian product represents the entire real plane, two-dimensional surface. Now, if two such lines which are in the plane of f intersect in the real plane, that is, they are not parallel, then they intersect somewhere, then this point, say its coordinates are alpha and beta, then this point lies in the plane of f. This we have already proved. And we have also mentioned that this is not quite the situation when instead of two lines, a line in the plane of f and a circle in the plane of f intersect. We know what a line in the plane of f is. Now, a circle in the plane of f is a circle in the real plane which has some radius r that belongs to f, and also it has some center whose coordinates belong to f. In other words, this point belongs to the plane of f. Now, we are going to look at this situation today, and this is the exercise we have to solve for that. So here what we have to do, prove that a line in f, that means one such line, and a circle in f which intersect in the real plane. You can see that this is intersecting, these are intersecting at 2 points. They may intersect at 1 point also, which will be precisely the case when the line is a tangent to the circle at that point. Then they do so at a point either in the plane of f. So this point may lie in this Cartesian product or in the plane of this extension of f, or it may lie here. Where gamma is a positive number in f. So gamma is some positive real number and gamma belongs to f. Now we have to prove this. So let's see how we can do that. Let me start the solution here itself. We have also proved some other things, namely the structure of the equations of such geometric objects when they are lines or circles in the plane of f, namely the coefficients that are involved in those equations, the constants that you get in those equations. are elements of F. Consider the line ax plus by plus c equal to 0 and the circle x square plus y square plus px plus ey plus f equal to 0 in F means in the plane of F. Which are intersecting, of course, because such objects we have to consider, which intersect at this point, say, in the real plane means in R2. And we can, of course, have two such points of intersection, in which case this is one of them. We mentioned that here. If the line and the circle intersect at 2 points in R2, our point is one of them, one of these 2 points. Okay, now the fact that these are lines and line and circle in the plane of F already tells us that A, B, C, D, E, F, these are all going to be elements in the field F, considering all the things we proved previously. So we write, we know that these real, after all, these are all real numbers, but in particular they will belong to F. D, E, F, all of them belong to F. Okay, now we are going to consider two cases depending on whether A is 0 or A is non-zero. If A is equal to 0, if A is 0, then B has to be non-zero in order for the line to be a line actually. Then B is but before the, okay, I forgot one thing. Before we can do these things though, we can put the coordinates here in these equations and the equations will be satisfied, because this is the point of intersection of these two objects. So we write next, we have A alpha plus B beta plus C equal to 0. And alpha square plus beta square plus D alpha plus E beta plus F equal to 0. Now we consider those two conditions. If A is equal to 0, then again the line has to actually be a line, so B has to be non-zero. because what could happen if B is also 0? Then C is also forced to be 0, and that is not the equation of any line. By the way, let me just stop here itself and let us just think of this equation. Say A is 0 and B is also 0, so C is forced to be 0, and the equation looks like this. What does this represent? Can you see that? Obviously, for any two real numbers, or in other words, for any such ordered pair in R2, this equation is satisfied. So this equation represents the entire plane, and that obviously is not a line. So that's why we need B to be non-zero when A is 0 in order to avoid this thing. Okay, so if A is 0, then B is non-zero. And so what do we get from this? We get this. Beta equal to minus C divided by B. Clearly, beta belongs to F, because C, B, all these things are coming from F. F is a subfield of R, and additionally B is non-zero, so this additive inverse of C over B is going to be in F. Now, if we use this value of beta here in this equation, then what do we get? Alpha square plus C square divided by B square plus D alpha minus EC divided by B plus F is equal to 0. This implies what? If we manipulate this a little bit, multiply throughout by B square, we then get B squared alpha squared plus DB squared alpha plus C squared minus ECB plus B squared F. This is equal to 0. So you can see that alpha satisfies this quadratic equation. Or let me write accordingly. Thus, alpha is a root of, should I write root, or let me write alpha is a solution to the quadratic equation b square x square plus db square x plus c square minus ecb plus b square f equal to 0. I hope I have done the calculation correctly. Let me see here. I have it written here in front of me. B square alpha square plus db square alpha plus c square minus ebc plus b square f. Yeah. Now something else about alpha is also known. We already know that alpha is real. Okay, alpha is real. Since alpha is real, so what does that tell us? That does not immediately tell us that the discriminant of this quadratic expression should be non-negative. But well, it does tell us that, but why? How? That's because you know that in such a quadratic equation where all the coefficients are real numbers, the complex roots occur in pairs of this form. If z is a complex root, then its complex conjugate is also a root. So that is why if you have obtained one real root alpha, then the other root, there is only one other root because it's a quadratic equation, a 2-degree equation, cannot be a non-real complex number. It has to be also be a real number. So that's why the discriminant has to be non-negative. Since alpha is real, so which actually means what? It means that there can be no non-real complex root, and that's why the discriminant has to be non-negative. There only real roots are there. That's why the discriminant has to be non-negative. We must have, we are going to give the discriminant a name also, gamma 1. So what will it be? Square of the coefficient of x, that is d squared b to the power 4 minus 4 times the coefficient of x squared times the constant term, c square minus ecb plus b square f. This has to be non-negative due to this realness. Now that means gamma 1 can either be 0 or it can be positive, a positive real number. Now if gamma 1 is equal to 0, then what happens to alpha in that case? Okay. I have written the discriminant though, and let me write the root also, and then let us write what happens if gamma 1 is 0 and what happens if gamma 1 is positive, because that way we can see what is happening to alpha. We have, so alpha in terms of the coefficient, I mean if you use the quadratic equation formula, then what do you get? Minus db square plus or minus, because we don't know which one it's going to be. So this will be what? Gamma 1 divided by 2 b square. Yeah, now we can write, if gamma 1 is 0, then alpha becomes what? This term vanishes, b square and b square cancel out. Keep in mind b is non-zero, so you just get d over 2, and this definitely belongs to f. because D is in F. On the other hand, if gamma 1 is positive, then you look at alpha. Can I directly write this? I can. Why? Because all these numbers that you see, D and B, 2, these are all in F. And one more thing, why is 2 in F? Here also we need 2 to be in F in order to have this conclusion. That is because F is a subfield of the field of real numbers, and we know that any such subfield contains all the rational numbers within itself. So 2 is in F. So all these things are in F, and now in order to accommodate square root of gamma 1, we have attached it to F and we are considering that extension. So all of these things ultimately belong to this extension of F, and that's why naturally alpha belongs to this. There is one more thing to note. Note that gamma 1 is an element in F because it is formed by all the ingredients are elements in F. That's why this element is also an element in F. Okay. So you can see that when this gamma 1 is 0, then alpha and beta are both in F. In other words, that point of intersection alpha comma beta is a point in the plane of F. But when gamma 1 is positive, then alpha belongs to this quadratic extension. Beta is always in F, but in particular, beta also belongs to this because this contains F inside of it. So in this case, the point of intersection alpha comma beta belongs to the plane of this extension of F. And now we consider the case A where A is non-zero. Next, let A be non-zero. Then what happens? In this case, from the first equation, that is A alpha plus B beta plus C equal to 0, we will be able to find out alpha because A is non-zero. And what do you get in place of alpha? You get minus B beta plus C divided by A. So that is alpha. And in this case, you can see that alpha belongs to F. Can we say that alpha belongs to F? We cannot immediately say that alpha belongs to F, no? Because beta is there. B, C and A are of course coming from F, but beta is there. Now we will have to say something about beta because then only we can conclude something about where alpha is coming from. Okay, so let us now see what happens if we put this value in this equation. In this case, we can find alpha, but we can't immediately say anything. So, alpha squared, that means the very first term is this, B beta plus C whole square divided by A square plus beta square plus dx d alpha, so that means minus d over a times b beta plus c plus ef, it's not ef, d alpha e beta plus f is equal to 0, and we will now have to bring this to the form where we can see that it's a quadratic expression in beta. Now if we multiply, the first step is of course we have to multiply throughout by a square, and also we can expand the square simultaneously, so that gives us b square beta square plus 2bc beta plus c square plus a square beta square minus dA. If I also do the multiplication simultaneously, because if you multiply by a square, you will have dA outside, minus dA actually. By that, if you multiply these two terms, then you get minus dAb beta minus dSc, and then with these two terms you will have a square f equal to 0. Okay, now the beta square terms, if we collect them together, we have this. Then the terms having beta, what are they? This one, and this one. So we can write, you can write in any manner you want, a square e plus 2bc minus dab times beta, and then the terms which are I should not say constant, but which do not involve beta in any way, plus c square, then minus dac, and then this one plus a square f. And before I proceed any further, let me see I have really written the correct one or not. A square plus b square times beta square plus a square e minus adb plus 2bc, a square e minus adb dab, same thing, plus 2bc. Okay, and the other term is c square minus adc plus a square f. Okay, yeah, here also thus beta is a solution to the quadratic equation x square plus a square e plus 2bc minus dab x plus c square minus adc plus a square f equal to 0. Again, because beta is real, same argument. Since beta is real, we must have, so the discriminant of this one, this quadratic expression, we are going to name it gamma 2. This one is going to be a little big, but we do not have to do anything with it. We just have to mention it once. Square of this a square e plus 2bc minus dab square minus 4 times this times this. This has to be non-negative. We could have just simply written the expression for beta after having this equation, but that would make things big. Now that we have a name for the discriminant, we can write it in a manageable manner. So we have beta equal to, still it will be a little big because this itself is somewhat large, a square e plus 2bc minus dab plus or minus square root of gamma 2 divided by 2 times a square plus b square. Note that now because a is non-zero, this denominator cannot be 0 because it's a square plus b square. Even if b is 0, there is no problem. Okay, now if here also two cases arise, gamma 2 is either equal to 0 or greater than 0. If gamma 2 is equal to 0, then what is beta? Beta will be dab minus a square e minus 2bc. This of course belongs to f. And also do not forget that we have to conclude the thing about alpha as well. Minus b beta plus c divided by a. This was alpha. So if beta is in f, then this expression also is in f. On the other hand, if gamma 2 is greater than 0, then beta belongs to this extension of f, and also in that case naturally alpha would also be there. And just like gamma 1, gamma 2 itself is in f, because in the expression for gamma 2 there is no square root or anything. It just involves addition, ordinary addition, subtraction and multiplication of real numbers, not even division. So all the ingredients are in f, so this expression would also be a real number in f. And that's just it. This completes the solution and it proves the claim. Now after this, we have one more case also to look at. That case is this. I think in the previous video I mentioned about this. There are two circles which intersect in the real plane, either like this or like this. Okay, you have to understand that there is only one point of intersection. In that case also, this is the situation, that is, these points of intersection or this single point of intersection, they are either in the plane of f or in the plane of f square root of gamma for some positive real number gamma in f. And to prove this, we do not need to do anything like this. This itself can be used to conclude that. That is because when two circles intersect, that also turns out to be the intersection of any one of them and a straight line, which is what we have considered here. So we are going to write like this, or rather Herstein has written like this. Next. When two circles in the plane of f, of course, not just any two circles, in the plane of f intersect in the real plane, their intersection can be realized as the intersection. Of either of them and a line in the plane of f. Like this. If we consider two circles, say x square plus y square plus a1x plus b1y plus c1 equal to 0 and x square plus y square plus a2x plus b2y plus c2 equal to 0 in the plane of f, which is equivalent to having all those coefficients in f, that is all the ai's and all the bi's, all the ci's also. That intersect in the real plane then that is also the intersection of any one of them with the line, with this line. And you can see that this is a line in the plane of f, because these coefficients are all coming from f, those constant terms. So these differences also are in f, which means this is a line in the plane of f. Note that the above line is a line in the plane of f. So this tells us, all of these things ultimately tell us what? Let us see. So let's summarize briefly what we have got so far. We have the field of real numbers and say f is any subfield of A. Then of course f has the field of rational numbers inside of it as its own subfield, which in this text is being denoted by f0. And we are going to use this in whatever comes next after all these things. Now, say you have a line which passes through 2 points, and the coordinates of both these points, all of them are coming from f. In other words, these 2 points belong to this subset of the two-dimensional plane, and that subset is called the plane of f. It turns out that the equation of any such line is of this form, where A, B, C, these are elements in f. Conversely, any such line also is a line in the plane of f. When it comes to circle, say you have a circle whose radius is coming from the subfield f. Radius non-negative, in fact you can take positive radius also, no need to consider zero radius, and whose center is in the plane of f. Such a circle is called a circle in the plane of f, and we have seen that the equation of any such circle looks like this. Where D, E, F, these are all elements in f. Next, what we investigated about the nature of the points of intersection of these objects. We have seen that when you take two lines in the plane of f that intersect somewhere in the real plane, then that point is a point in the plane of f. And today we have seen that if a circle and a line intersect, both of which are in the plane of f, both the line as well as the circle, then these points of intersection either belong to the plane of f or to the plane of such an extension of f for some positive real number gamma which itself is in f. And this last part shows that if two such circles intersect, then their points of intersection also behave like that. They are either here or here. Now in the next upload on this part, that is field theory, we are going to apply all these things to that special subfield, the field of constructible numbers. And you already know the definition of constructible objects that we have given, we already have. There, the allowed operations involve such objects, that is points, lines, circles, and their points of intersection are the new constructible points. Lines that you can draw through them are constructible lines. So we are next going to see how this new information is going to fit in with those things, or in fact what this new information is going to tell us about those constructions. And from the look of these extensions, you can see that they are quadratic extensions. Okay, the degrees of these extensions over f are 2. Well, if gamma turns out to be a number for which this belongs to f itself, then the degree of this extension is just simply 1. In that case, this is nothing but f. But in other cases, the degree is 2. So these degrees are 1 or 2. So every time you make new constructible objects starting from something, you increase the degree by 2. So that is ultimately going to give us a necessary and sufficient condition that a real number is constructible, and we will get that condition in the next video. So I am going to stop things here itself for tonight, and we are in 2 or 3 more at most 2, not 3. We are going to finish the theory and then we can solve the problems. Okay, and tomorrow also we have an upload, and tomorrow let us solve algebra problems from Lee's algebra again. So see you tomorrow with that. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.